We have seen that if S is an orthonormal set, then any vector W in the span of S can be easily written as B1 inner product with W over B1 times B1 plus BK inner product with W over BK times BK. This is true under the assumption that S is an orthogonal set. But what about if we have that S is not necessarily orthogonal, it's just a linearly independent set? Then we would like to have a collection T, let's say, of vectors u1, uk, such that this T is orthogonal. It is an orthogonal set, and the span of T is equal to the span of S. The Gram-Schmidt procedure guarantees this. It allows us to move from a set that is just a linear independent set into a collection of k vectors that form an orthonormal set. Let's see the procedure. Then this is the theorem. Let's suppose that S is a collection of k vectors and they are linearly independent. And then if we make U1 equal to B1, U2 equal to B2 minus U1 B2 over U1 U1 U3 equal to B3 minus U1 B3 U1 minus U2 B3 inner product of U2 and if we keep going with this procedure, in general U sub I is just B sub I minus U1 BI U1 minus UI minus 1 BI, the normal square of UI minus 1 times UI minus 1. Then this collection of new vectors, let's say, then T equal to U1 up to UK is an orthogonal set. And the span of S equal to the span of T. The proof is somehow straightforward. For example, we can see that the dot product of U1 and U2 is equal 0. Let me just check some part of the proof. It's done by induction, but we're just going to check a few things here. When I do U1 dot product with U2, U1 dot product with U2, this is U1 dot product with B2 minus U1 B2 over U1 and remember that we have this property that when we do the dot product of B with alpha W, then the alpha goes out like this. And also just, we don't need this one, but Remember that if the alpha is in the first vector, is multiplying the first vector, then the property would be alpha conjugate BW. Then here, this is an alpha, is in the second entry, then it goes out. Then here we have a U1 B2 minus, this is a number, this is a complex number, U1 B2 over this complex number times U1 U1, but here these two cancel out, and then we get that this is 0. Once we have shown that this inner product is 0, then we can show that U1 inner product with U3 is 0, and U2 inner product with U3 is equal to 0. In the proof of these two, we need to use the fact that the inner product of U1 and U2 is equal to 0. And then the proof will follow by induction. Let's do an example. Let's consider the following set of three vectors. 1, 1 plus I, 1, negative I, 1, 1 plus I, and 0, I. This is our sets B1, B2, and B3, and we can check that these vectors are linearly independent. Then the idea is to find a set T equal to U1, U2, U3, such that the span of S is the same as the span of T, and that this set is an orthogonal set. Then let's start the procedure. U1 is equal to B1, which is this one. This is B1 equal to U1. Now, U2 is equal to B2 minus U1 B2 over U1 U1 times U1. Notice that when we are working with complex numbers, the inner product is not commutative. Then it's important the order. First, it comes the U1, which is equal to B1, and then the new vector. You see here is first the U's, and then the V's. And then let's do some of these that are here. Then what is U1, U1? U1, U1 is 1 times 1 plus 1 minus I times 1 plus I plus 1 times 1, and this is just 1 plus 1 minus I squared plus 1, and this is equal to 4. And this is 4, and U1 B2, this is B2, and this is U1, then is the conjugate of 1, which is 1 times negative I, plus the conjugate of this, which is 1 minus I times 1, plus 1 times 1 plus I. And this is negative I minus I will be minus 2I plus I. It's just minus I. And here we have 1 plus 1 is 2. 2 minus I. Then this is just V2, which is negative I, 1 plus I, minus 2 minus I over 4 times U1, which is 1 plus I, 1. Let's do this. This is, let's multiply. This is negative I, 1 plus I, minus 1/4 of 2 minus I. Now here it goes 2 minus I times 1 plus I, and this is 2 plus 2i minus I squared. This is positive 1 plus 2 is 3 plus I. And this is 3 plus I. And here, this 2 minus I times 1 is 2 minus I. Let me erase this. And let me erase all of this. Then this is equal to negative 2 quarters. And then this is positive 1 quarter minus 1 is minus 3 quarters of I. And here we have 1 minus 3 quarters is just 1 quarter. And here we have 1 minus I over 4. And finally we have 1 minus 2 quarters is just 2 quarters. And I plus I over 4 is 5I over 4. Then we have that U2 is equal to, let me write it down here, 1 quarter of negative 2 minus 3I, 1 minus I, and 2 plus 5I. Let's compute now U sub 3. U sub 3 is equal to B sub 3 minus U1 B3 U1 U1 times the vector U1 minus U2 B3 minus U2 U2 times U2. But let's see what is U1 inner product with B sub 3. U1 inner product with B sub 3. This is U1 inner product with B sub 3. B sub 3 is this one. Then we get 0. And then here we have plus the conjugate of 1 plus I, which is 1 minus I, times I, and then plus the conjugate of 1, which is just 1, times I. And this is I minus I squared plus I, and this is 1 plus 2I. Then, and what is U1 U1? We already computed. U1 U1 is equal to 4. Therefore, this part changes into 1 plus 2I over 4. Now let's compute U2 V3. U2 V3 is equal to 1 quarter the conjugate of this negative 2 plus 3I times 0 plus 1 quarter the conjugate of 1 minus I, which is 1 plus I, times I, plus 1 quarter times 2 minus 5I times I. And this is just 1 quarter times I plus I squared plus 2I minus 5I squared. This is 5 minus 1 is 4. Then this is 1 quarter times 4, and I plus 2I is 3I. This is U2 B3, and the inner product of U2 and U2 is 1 quarter times 1 quarter. We're going to have a factor of 1/16 everywhere. And then when we do the conjugate of this complex number with the complex number itself, I'll get 4 plus 9. Here I get 1 plus 1 and here I get 4 plus 25, and this is going to be equal to 44 over 16. That means that this factor here is just 1/4 times 4 plus 3i over 44 over 16. This is 11. This is 11 over 4, and then I have 1 over 11 times 4 plus 3i. Then I can replace this with 1 over 11, and here 4 plus 3i times u2. u2 is 1/4 of -2 minus 3i, 1 minus I, and 2 plus 5i. And u1 is 1 plus I, and 1. Then u3 is equal to v3, which is 0i minus, let's factor out 1/4 here, 1/4 factor of 1 plus 2i. Now this times this is 1 plus 2i times 1 plus I is 1 plus I plus 2i plus 2i squared. This is -1 plus 3i, and this times 1 is just 1/4 of 1 plus 2i. Now this is minus 1 over 44 times 4 plus 3i times -2 minus 3i. This is -8 minus 12i minus 6i minus 9i squared, and this is positive 9 minus 8, 1, and minus 18i. Now 4 plus 3i times 1 minus I. This is 4 minus 4i plus 3i minus 3i squared, and this is positive 3 plus 4 is 7, and this is 7 minus I. And finally here 4 plus 3i times 2 plus 5i. This is 8 plus 20i plus 6i plus 15i squared. This is -15 plus 8 is -7 plus 26i. And we can do the arithmetic here in the same way that we have been doing this, and then we can check that this is 1 over 11, -3 minus I, 1 minus 3i, -1 minus I. Then we have found the three vectors, u1, which is this, u2, and this is u3. We can check that these three vectors, they form an orthogonal set. Notice that we have to be careful when we are working with complex numbers because the inner product does not commute. The same procedure will work in general if we have just real numbers. And when we're working with real numbers, we don't have to be careful about the order. Let's just do an example. Let's suppose that we have S equal to 1, 0, 0, 1, 1, 0, and 1, 1, 1. These three vectors are clearly linearly independent, and let's do the Gram-Schmidt process to see what we get. Then this is the vectors b1, b2, and b3. This is u1, right? u1 is equal to b1. Now, what would be u2? u2 is equal to b2 minus u1 b2 over u1 u1 times u1. In this case, u1 inner product with u1 is just 1, and u1 inner product with b2, if we do this inner product, we also get 1. Therefore, u2 is v2, which is 1, 1, 0, minus 1 times minus 1, 0, 0. And this is 0, 1, 0. Finally, u3 would be equal to, let me erase this part here, let me do it here, u3 would be equal to b3 minus u1 inner product with b3 over u1 u1 times u1 minus u2 inner product with b3 over u2 u2 times the vector u2. Let me just erase all of this, and we have that u2 is the vector 0, 1, 0, and then clearly, and then u3 is just v3, which is the vector 1, 1, 1, minus u1, that product with v3 is 1, and u1 over 1 is 1, then this is 1, times the vector u1, which is 1, 0, 0, minus u2, that product with v3, the dot product of these two is 1, and the dot product of u2 with itself is also 1, and here we have minus 1 times u2, which is 0, 1, 0. And then we get that this is just 0, 0, 1. Then in this case, if we start with these three vectors, we end up with the canonical basis. This is u1 is 1, 0, 0, u2 is 0, 1, 0, and u3 is 0, 0, 1.